Good day and welcome to my Campus Guide channel. Today we are talking about semiconductors under basic electronics. To talk about semiconductors, you can't do this without considering the atomic structure of elements. Every material is made up of one or more elements, and these elements are composed of atoms. These atoms come with different structures. So this brings about the different structure and shape of elements or materials we have. So generally, we can divide or group all these elements into three. Grouping of these elements will depend on the valence electrons of these atoms. What do I mean by the valence electrons of these atoms? So these electrons that are found on the outermost orbit of an atom is called a valence electron. And the number of electrons contained on this outermost orbit is highly considered in this study of electricity, because the number of electrons on the valence orbital or on the outermost orbit determine the physical and the chemical property of the material. So whenever you find any atom with less than 4 valence electrons, then this atom or material is likely to be a metal or a conductor. What do I mean by that? Whenever we check the electronic configuration of an atom, and on the outermost orbital of this atom, it has less than 4 valence electrons, then that material is a conductor or is a metal. Examples of these materials are sodium, magnesium, and aluminum. But whenever we have an atom or a material with more than 4 valence electrons, then that material is an insulator. Atoms on the outermost orbital, it needs 8 electrons to make an octet or to make it complete. So whenever the atom at the outermost shell is more than 4, then that atom is likely to be an insulator. Examples of these atoms or materials are nitrogen, sulfur, and neon. But whenever the number of electrons on the valence orbital are exactly equal to 4, then the conductivity or the ability of this material will lie between a metal or a conductor and an insulator. So whenever the number of valence electrons of an atom is equal to 4, then that material is a semiconductor. That means its conductivity lies between a metal and an insulator. That is a conductor and an insulator. So example of these semiconductors are carbon, silicon, and germanium. But in our study, we will use a theory called the energy band theory to explain why these materials have such properties. That is, some can easily conduct and others are not able to conduct, and the semiconductor too is having its ability between a conductor and an insulator. We will use the energy band theory in this study to explain all these phenomena. The energy band theory. In solids, atoms are held by forces from other atoms. So this means whenever an atom is in an orbit, there are other forces around it that keeps it. That means we can call this number of forces or energies the energy band. So this means when we talk about an energy band, then we are talking about a range of energies that an electron can have or possess due to the forces experienced from the neighboring atoms. So in this energy band theory, you will get to know or hear about a valence band and a conduction band. Don't worry if it's your first time hearing this thing. By the end of this video, you will understand all these terms and use them as a professional. We will use this diagram here to explain the energy levels we have in the energy band theory. When we look at this diagram here, we have the valence band, we have a forbidden band, and we have a conduction band. What do I mean by a valence band, a forbidden band, and a conduction band? Whenever an electron is on the outermost orbital, we call it a valence electron. So these valence electrons are found in the valence band. And for a material to conduct electricity or for a material to have a low resistivity of electricity, electrons at this valence band must gain energy to overcome this gap here. That is the forbidden gap. So for a material to conduct, the valence electron has to gain energy so that they become much excited to exceed this forbidden gap here. So the range of energies possessed by these valence electrons are called the valence band, and the range of energies possessed by these free electrons are called the conduction band. And the forbidden gap separates the conduction band from the valence band. For an electron to conduct, it must gain enough energy, that is ionization energy, to overcome this vacuum here, which is the forbidden gap. So let's look at how the energy levels are grouped or are presented for these three types of materials we have already grouped. We said we have insulators, conductors, and semiconductors. From this diagram, what can we deduce from it? We can see for insulators, we are seeing a very big gap over here. What is written there? It's saying there is a large difference in energies between the two bands. So what do they mean by this? You see for insulators, they have a very big or large forbidden gap. So for this reason, no matter how an electron is excited at the valence band, or no matter the energy gained by an electron at the valence band, it finds it very difficult to overcome this gap because the gap is very large. So this accounts to the high resistivity of electricity in insulators. Because they have a very big or large forbidden gap, electrons are not able to make it to the conduction band, and current can only flow when electrons get excited to overcome this vacuum, which is the forbidden gap to the conduction band. Let's look at the diagram for the conductors. In conductors, we can see the conduction band and the valence band are overlapping. So this zone here can be called an overlapping zone. So from this diagram, we can see there is relatively no space or no gap for electrons to overcome. So the minimum or the small amount of energy gained by these valence electrons, they just move on to the conduction band. So this is accounting to the low resistivity of electricity in conductors because there is an overlapping between the valence and the conduction band. Electrons in the valence band finds it very easily moving to the conduction band. Immediately they get excited. Now let's come to the semiconductors. From what is here, we are saying small energy difference between the valence band and the conduction band. So meaning in semiconductors, there is a small forbidden gap to be overcome by the valence electron. So the least amount of energy or the least excitement by a valence band will push it across the forbidden gap to the conduction band. So this is why we are saying the semiconductor, its ability lies between a conductor and an insulator because it has a very small forbidden gap. So you just need to apply a few energy or some little amount of energy to overcome the forbidden gap. But when you come to the insulator, it has a very large or big forbidden gap. So electrons find it very difficult to overcome this forbidden gap even when they are excited. Conductors. So we have summarized everything here that conductors have no forbidden gap. The valence and the conduction band overlap, allowing a very large number of electrons available for conduction at extremely low temperatures. And also for insulators, an insulator has a wide forbidden gap and thus few valence electrons have efficient energy to become excited to the conduction band. That is, it is unlikely even at room temperature for electron to get excited to the conduction band, and insulators conduct very poorly. Example of these insulators are rubbers, glass, wood, etc. In terms of energy band, insulators are those substances in which their forbidden gap is very large. So now let's see the semiconductors. Let's talk about the semiconductors. Semiconductors are materials whose conductivity lies in between that of a conductor and insulator. They have a narrow forbidden gap. So example of these semiconductors are silicon, germanium, selenium, gallium and arsenide. Comparatively, smaller energy is required to push the electron from the valence band to the conduction band. At low temperatures, the valence band is completely filled and the conduction band is completely empty. What do I mean by that? I mean whenever there is low temperature in semiconductors, at a very low temperature, there is no way electrons can gain much energy to overcome this narrow forbidden gap. So at low temperatures, the valence electrons will remain at the valence band, and even those that are already excited to the conduction band will all fall back to the valence band at very low temperatures. Today, our focus is much on the semiconductors because we as engineers, we want to modify materials and use materials like the semiconductors because its conductivity is lying between a conductor and an insulator. So we want to use such materials to produce items or to produce our things so that it only conducts when we want it to conduct and it remains an insulator when it is allowed to rest or when it is not excited. So now let's look at the classification of a semiconductor. A semiconductor can be further classified into two groups. We can group semiconductors into intrinsic semiconductors and extrinsic semiconductors. What do I mean by intrinsic semiconductors and extrinsic? When we say a semiconductor is intrinsic, this means we are talking about the pure semiconductors. A semiconductor is said to be intrinsic when it contains no impurity or no crystalline defect. So meaning intrinsic semiconductors are crystalline semiconductors. They have no impurity. That is at absolute zero. Every electron is at the lowest energy. So when there is a low temperature, all the electrons move down to the valence band. They occupy the valence band and the conduction band remains empty, but at room temperature, the electrons acquire thermal energy, or that's the ionization energy, and move to the valence band. Whenever electrons become excited in an intrinsic semiconductor, they start to move. And bear in mind, there is a flow of current only when there is movement of electrons. But now we are introducing something we call a hole. One may say, what is a hole? Whenever these electrons at the valence band or the valence orbital, they gain energy, they move. Whenever they move, they leave a vacancy behind them. They were already assuming a position on the orbital. So whenever they move from the valence band to the conduction band due to their excitement, they leave a vacancy behind them, which is termed in our study here as a hole. Now the electron has gained enough energy, so now it becomes a free electron. It has broken the bond it is forming with neighboring orbitals. We know there is a covalent bond between these neighboring electrons. So when an electron at the valence band gains this energy, it breaks this covalent bond and therefore become a free electron, and also leaving behind a free hole at the valence band. This process in our study, we will call it electron hole pair. So whenever an electron becomes excited and move from the valence band to the conduction band, leaving a hole at the valence band, we will term it an electron hole pair in our study. So let's explain this with a diagram. So in intrinsic semiconductors, you see we are saying semiconductors have 4 electrons in their outermost orbital. So now we can see these 4 electrons forming bonds with neighboring orbitals. But let's see this electron here. This electron here was assuming this position, but after it gained energy, it became excited and moved away from this valence band, and the bond forming, which is the covalent bond here, it has moved away from it. So after it getting excited, it left a hole here, which is a vacant position to be filled. So you will term this place as a hole, and we will term the excited electron as a free electron. Now let's look at the other classification of semiconductors, which are extrinsic semiconductors. These extrinsic semiconductors are basically the normal intrinsic semiconductors we know. But we know for intrinsic semiconductors, we are saying they are in their pure state, or they have no crystalline defect. So meaning the number of electrons is equal to the number of holes in the intrinsic. But now we want these intrinsic semiconductors to conduct electricity. For this reason, we have to add some amount of impurity. What do I mean by we add an amount of impurity? We are adding an atom or an element to this to increase the number of electrons or to increase the number of holes in this intrinsic semiconductor. So whenever we add an impurity to an intrinsic semiconductor, it ceases to be an intrinsic semiconductor, and therefore we start to call it an extrinsic semiconductor. So the process of adding this impurity in our study here will be termed as doping. So whenever we see doping, we say doping is an act of adding an impurity to an intrinsic semiconductor. So the element or the atom we are using for this doping, or the element serving as the impurity here, will be called the dopant. So depending on the type of impurity we want to add to this intrinsic semiconductor, we can further classify extrinsic semiconductors into N-type extrinsic semiconductors and P-type semiconductors. What do I mean by N-type and P-type semiconductors? For N-type semiconductors, we add a pentavalent impurity. What do I mean by pentavalent impurity? When we see an impurity or an element is pentavalent, that means it has 5 electrons on the valence orbital. So on the outermost orbital of this element or these atoms are 5 electrons. So now we are bonding these new 5 electrons with the 4 electrons we already have in the intrinsic semiconductor. So after bonding 4 orbitals with 5 orbitals, let's look at the ratio 4:5. So meaning each of them will bond to one another. There will be a free electron now. So example of these pentavalent impurities are phosphorus and antimony. So now you dope this intrinsic semiconductor with a phosphorus or antimony which has a pentavalent or which has 5 electrons on their outermost orbital. So now because the ratio now is 5:4, there will be a free electron. Therefore, we term these N-type semiconductors or the pentavalent impurities we are adding, we term them as donors because they tend to donate their extra electron to the intrinsic semiconductors. So we term these pentavalent impurities or elements as donors because they provide an extra electron to the semiconductor's crystalline structure. So now because we have a free electron now, or we have an extra electron in the N-type semiconductors, we say the number of electrons is more than the number of holes. So we term it under basic electronics as the electrons are majority carriers. So in other words, the holes are minority carriers. So in this study, we can summarize everything here that in N-type semiconductors, we have extra electron than holes. So we say electrons are majority carriers, and N-type semiconductors have a negative charge. Take this from me, N-type semiconductors, they possess a negative charge. Let's explain this with a diagram. So now this is example of a bonding in the n-type semiconductor. So this element or impurity is a phosphorus. So now we add the phosphorus impurity or the pentavalent impurity to the intrinsic semiconductor, and there will be a free electron now. So this is making the number of electrons more than the holes in this n-type semiconductors. So in n-type semiconductors, we see the electrons are majority carriers and the holes are minority carriers, and n-type, they have a negative charge. Now let's look at a number of pentavalent impurities or pentavalent elements. We can have phosphorus, antimony, and arsenic. Now let's look at the other type of extrinsic semiconductor. Now p-type semiconductors, we are doping with a trivalent impurity. What do I mean by a trivalent impurity? Meaning we are doping, or the dopant we are using here has 3 valence electrons on the valence band, or it has 3 electrons on the outermost orbit. So here, because it's not even up to the 4, which is bonding with the intrinsic, we call these p-type semiconductors, or the dopants here, we call them acceptors, because they are not donating, because they are not even up to the 4 we need to bond with our intrinsic semiconductor, or the electrons of this intrinsic. So we call the trivalent impurity here, we call them acceptors, because they leave a hole in the semiconductor's crystalline structure. Hence, in p-type semiconductor, we see the number of holes are greater than the number of electrons. So in other words, we see holes are majority carriers in the p-type semiconductor. So example of these trivalent impurities or trivalent elements are boron, indium, and gallium. Let's look at a summary of all we've learned today. We said in pure state, a semiconductor is an excellent insulator. So when a semiconductor is there and we've added no impurity, or when it's in its pure state, it can serve as a very good insulator. And we also said the most commonly used semiconductors are silicon, the most commonly used one. So whenever you get a problem, or you are given a problem to solve, and the semiconductor given you is not named, we assume it to be silicon, because it's the most commonly used in basic electronics. And also we said semiconductor materials can be doped with other atoms to add or subtract their electrons. So what that means is that we can add a donor or an acceptor to an intrinsic semiconductor to enhance its conductivity. So we said whenever we add a donor to the semiconductor, it becomes an n-type extrinsic. Whenever we add an acceptor, it becomes a p-type extrinsic. And we see for n-type, it has a negative charge, and that is the electrons are majority carriers. And we said p-type semiconductors, they are type of extrinsic semiconductors that has a shortage in electron. That is, they have more holes than electrons. So in p-type semiconductors, we say the holes are majority carriers and they carry a positive charge. And we talked about what a donor is. So the donor is an impurity, or the donor element is the element that increases the number of electrons, while the acceptor element or the acceptor impurity is the one that decreases the number of electrons or that increases the number of holes. So we said N-type materials contain more electrons, P-type materials contain holes than electrons. And when we say a majority carrier, then we are talking about the most abundant carrier over there. So when we take N-type, the most abundant is the electrons. So meaning the most abundant carrier we are talking about is what we mean by a majority carrier. So we also said when we say an intrinsic semiconductor, that means it has no crystalline defect and it has no impurity. So that means the number of electrons is equal to the number of holes. But for extrinsic, we dope it with either a pentavalent or a trivalent element to improve on its conductivity. I believe this information was helpful, and I would like you to subscribe if you are new to this channel and share this video massively. Thank you.